Hello, today me and my friends going to present about our mini project for CA for the title 9. Design a 32-bit CPU with considering the 0 and carry flag register. The CPU can perform the following operation: logic XOR, logic AND, logic NOT, addition, shift right, and decrement. So me myself is Nivesha and my team members' name is Aishwarya Rao, Nishantini, and Sasmita. So the introduction of our mini project. In this mini project, the 32-bit CPU is designed to perform basic arithmetic and logic operation including XOR, AND, NOT, addition, shift right, and decrement. The CPU includes two flag registers, the 0 flag which is set when the result is 0 and the carry flag which is set during arithmetic overflow. These operations are fundamental to general purpose processor and are used widely in ALU arithmetic logic units.
My name is Nishantini Anaperempuan Desing. The objective of the mini project is to design and simulate a 32-bit simple CPU, to implement 8 logic and arithmetic operations, to include 0 and carry flags for result evaluation, and to verify CPU functionally through waveform simulation.
A very good day. My name is Sasmita Dr. Subramaniam and my matrix number is 231371770. So today I would like to continue my part of this mini project presentation where I'll be talking and presenting about the block diagram. So starting off with the question that we've gotten is to build, and the goal is to build a CPU of 32-bit operations of logic gates such as XOR and NOT, and with addition, shift register, and decrement. So all of this of 32-bit. So starting off with our input, where we have input of register A and register B of 32-bit, and next we have it the next operation we go on to logic XOR. Logic XOR operates on bitwise XOR, and then logic AND of 32-bit, it operates for bitwise and logic NOT operates for bitwise NOT. So only the logic NOT has the input from register A. Next, we have addition, that which is an adder, a 32-bit adder, which adds up the input from A and B. Next, we have a shift register, which shifts right by 1, a 32-bit shift right, and then a decrement of -1 of the input of 32-bit. So all of this goes into the multiplexer of 8 to 1 multiplexer. And since we have 6 operations that we have to handle, so we can't be using a 4 to 1 multiplexer. So we have decided to use a 8 to 1 multiplexer. And as you can see, we have left the 2 inputs just unused over there. And next, this multiplexer also have about 4 selectors. These selectors is what we can which we will choose the input, which we will forward it to the output. So there is selector 3, 2, 1, and 0. So next, the final one is the register C, which we have named as the final result of R, the output R in our coding. And we also have to look into the 0 flag and carry flag, which is also implemented in the coding but is not shown over here. So that's all for the block diagram. Thank you. So let's move on to the coding part of the main module. So over here we have declared a module as a mini project. So the module name is declared as a mini project, and we have also declared several inputs in here. So the first input of a 32-bit is A, and then the second input is B, same 32-bit. And then we've also declared uh, a 3-bit input of OP. OP means opcode. And then next would be an output of our register R. So we have named the output as R. This is also a 32-bit register. Next, we have also carried the output of register for zero flag and the output of register for carry flag. So next we are going to put in the coding for wire, the immediate wires. So there's a 32-bit wire for all the logic gates output. So starts with XOR out and then AND out and NOT out. So next we also have a wire of 32-bit for sum out. Sum out is for the adder. So we name it as sum out, and then there is this is decrement out. So it minuses 1. Next is shift right out. So it shifts right by 1. And then there is also wire for add carry and decrement carry. So next we go for the logic gates for XOR and NOT and also shift right. So we generate I as the data, and for this data it starts with 0 and we add 1 and until it reaches 32, the XOR and NOT goes through this bitwise operation. And if the I is less than 31, we have assigned the shift right output to actually add in 1. So it becomes, after every single cycle, it becomes 1 bit higher. And then next, else we assign the shift right output when it becomes exactly equals to 31, we make it a 0. So that ends this coding part here. So we continue with the next part of the coding, which is a 32-bit adder using only XOR and NOT logic. So we first declare the wire, the immediate wire of a 32-bit add sum. Add sum is the total output of the sum. And next is wire of a 33-bit of add carry chains. Add carry chain is a ripple carry adder, and we have assigned add carry chain to for as its initial to be 0. And next we have a for loop for the data where the same, if it is less than 32, we have it adding 1 after 1 and 1 with a wire of AXB. AXB is X A X or B, and then there's a C1, C2, C3, which is an end term of the carry flag. And then next we have wire of the OR. It's a not, but then it's an or implementation where not 1, not 2, not 3. And then and all is actually where this ends with this, which n1 ends with c1, and then or n2 end with c2, or n3 end with c3. So that's how and all is about. And this part of the coding is to calculate the sum, and then this part of the coding is to calculate the carry, and this one is the implementation of OR using the De Morgan. So we end the coding part here. Thank you so much.
Assign add carry equal add carry chain 32. This line assigns the final carry out from the 32-bit adder to add carry. Assigns sum out equal add sum. This line assigns the computer 32-bit sum to the output sum out. Wire 31 0 1 complement declares a 32-bit wire to represent a constant vector of all ones used to subtract 1. Wire 32-0 decrement carry chain declares a wire to hold the carry values for decrement operation. Next, assign decrement carry chain 0 equal 1b1. This line sets initial carry into 1 to perform A1 operation and generate block for looping logic. Okay, for I equal 1 smaller than 32 and I equal I plus 1 begin decrement. These lines indicate starts a loop to handle each bit, which is bit 0 to bit 31, and its name decrement. Wire sum D C1 C2 C3 declares wire for intermediate value in bit level full subtractor. Wire N1, N2, N3 and all declares wire for intermediate NOT and AND operation for carry. Next, assign 1 complement I equal 1b1 sets each bit of 1 complement to 1. This is binary 0 times f. Next, XOR sum DA 1 complement is calculates the first XOR for the current bit, and XOR decrement out sum D decrement carry chain is final XOR to get result bit. Next, and C1 AI1 complement. This line is part of a carry generation logic, and the next line is a second part of carry generation logic, and the third line is third part of generation logic. Next, NOT N1 C1 is inverts C1, and the second line is NOT N2 and C2 is inverts C2. NOT N3 and C3 is inverts C3. Next, N and all N1, N2, N3, this line applies De Morgan to get NOR results. And the next line is NOT decrement carry chain I plus 1 and all is to final carry out using De Morgan carry equals C1 plus C2 and plus C3. And lastly, need to ends the current iteration of the loop, and end generate is for end the generate of the block.
So for the coding part, for the line of assign decrement underscore carry equals to decrement underscore carry underscore chain 32, this line assign the 33rd bit index 32 of decrement underscore carry underscore chain to the signal decrement underscore carry. So for the ALU operation selection, for this line, a comment indicating the start of a ALU operation selection logic. For always at begin line, this define a combinational logic block that execute whenever any input changes. So for the case OP, for this line, start a case block based on the OP signal, typically a 3-bit operation selector. So for the line of 3B000 $R equals to XOR the underscore out. So this line indicates if OP is 000 assign result R to the output of XOR operation. So for the line of 3B001 double dot R equals to N out, this line indicate if OP is 001, assign result R to the output of N operation. For the next line of 3B010R equals to not underscore out, this line indicate if OP is 010, assign result R to the output of NOT operation. So for the 3B101 double dot R equals to sum underscore out, for this line indicate if OP is 101, assign result R to the output of add or sum operation. For the line of 3B110 double dot R equals to shift right out, this line indicate if OP is 110, assign result R to the output of shift right operation. So for the 3B111 double dot R equals to decrement underscore out, for this line it indicates if OP is 111, assign result R to the output of decrement operation. So for the default double dot R equals to 32 B0. So for this line, it indicates that if OP doesn't match any case, default the result R to all zeros. So then for the next line is AND case. For this AND case, this indicate as ends the case block. So for the zero flag line, it's a comma indicate logic for calculating the zero flag. And the next line for the 0 equals to R equals to and equals to 32 B0. For this line, the zero flag is set to 1 if result R is all 0, else 0. So for the carry flag line, it is a comma indicate logic for calculating the carry flag. So for the case OP, it start another case block for determining the carry flag based on the operation. So for the 3B101 double dot carry equals to add underscore carry. So this line is indicate for addition, carry flag is taken from add underscore carry. So for the line of 3B111 carry equals to decrement underscore carry. So this line indicates that for decrement, a carry flag is taken from decrement underscore carry. So for the 3B110 carry equals to A0 LSB before shift. Left the LSB is the least significant bit, so before the shift. This line indicate for the shift operation carry is the least significant bit LSB of input A before shifting. So for the default double dot carry equals to 1B0. So for this line, its default carry flag is 0 if operation doesn't require it. So after all this, then we put coding as AND case. So for this AND case is defined as AND the carry flag case block. At last, it's AND. So AND the always block, and overall we end the module. So for the AND module is just end the module definition in Verilog.
Hi everyone, my name is Aishwarya Rao, daughter of Manika Rao. Today I'll be presenting mini project title number 9, and I'll be explaining you the test bench part for this topic. Okay, let's go to the test bench part. Okay, As you can see from the test bench coding, I'll explain each line of this test bench coding. Okay, so let me explain. Okay, first the first line, which is the time scale 1 nanosecond and 1 picosecond slash 1 picosecond, it indicates that the time precisions. That's it. And then the second line is the module project, which is the module name lah of our project, mini project test bench. Okay, the third line, register 31, which is out input A and B is declares that 32 bits registers A and B inputs to be the DUT, and same goes to the second register, but this one is about the opcode, which is declares that 3 bits register opcode to select the operation, for example XOR gate, AND gate, and NOT gate. Okay, the third one, wire, which wire we need to connect. Okay, the wire, it will declares declares 32-bit wire R for the output result from the DUT, and the wire 0 carry flag is declares that the outputs. And also the part of mini project UUT, you can see there is a few operations under that. So from there you can see mini project instantiates the design under the test UUT, connects the part to the test bench var. Initial begin starts the initials block to run the test sequences, and the monitor everything is continuously printing the value whenever any variable in the list changes. And then the A time like the dollar time, and the A equals to B opcode, it's the sets the input value for the each test case, waits 10 nanoseconds. The what, as you can, the hashtag 100 is to wait 10 nanosecond before the next one. Okay, from the length you can see the following one. Test XOR command describing the next test is for the XOR operation, which is what's the operation, and the following thing lah, test for NOT gate and AND, shift right, decrement, and the last is stop for the stop simulation, and the end module ends with the test bench. This is the each coding that I explained for the test bench. And I also will be explaining for the output waveform. Let's check whether it's correct or not, the output we get. Okay, as you can see, I'll be explaining the output waveform. Okay, for the first line, it indicates it declares the XOR output. Okay, I'll be explaining the few columns of the output is whether right or not. As you from there you can see the output is, the rest of the output will be right lah. So I'll be explaining the first line was the first column. As you can see, 1 0, always XOR 1 0 is equals to 1. So the 1 0 again it will be equals to 1. Okay, the second one also same, 1 0 0 1 is equals to 1. 1 0 is equals to 1 again. So from here we can see the declare the output of the first row, first column is for X4 is successfully done. And then the second one for the AND gate, okay, as you can see, 1 0 is equal to 1 times 0 is equals to 0. So 0 times 0 is 0. So same as the second one also. For the third one, 1 times 0 is 0. 0 times 1 is also 0. So the second one also successfully declared as a the output is correct. And then the third one is NOT gate. So NOT gate, as you all can know, that the NOT gate is always invert. If you give a 1, it will the output will be invert. If the input is 0, the output will be invert as a 1. Okay. You can see the third one, the fourth, 1 2 3. Okay, the third one is also the NOT gate is okay. And then we move on to the fourth one, which is the addition output. Addition output, as you can know, 0 plus 0 is 0. So the 0 plus 0 is also 0. So the first column is declared is correct. The second column also the same. 0 plus 0 is 0. 0 plus 1 is 1. So from there you can see our addition output also is correct. And then for the shift right, that you have the opcode which is 110. So logically shift is more significant bit becomes 0 and the less significant bit becomes saved as carry. From this case, so as you can see, the shift right of carry is the less significant bit is saved as carry, which is 1. So our last line, you can see it's 1 increase step, so that is indicates it's 1 lah. So the second one also, the decrement, it's we get 1 -1 because it's a decrement. So our last input is also it's 1. You can see from the waveform. So done with full subtractor with logic using XOR and AND NOT gate. So to sum up everything, in the conclusion, our waveform is successfully, the output is successfully, it's based on the theory lah. It's not, it is matched with the theory. It's related to the theory. Okay. So now I'll conclude all this in my conclusion, which is that the conclusion is a simple 32-bit CPU was successfully designed with the logic and arithmetic capabilities. The CPU supports essential instruction and includes 0 and carry flags to indicate the computation status. The simulation validates each functions, making this CPU suitable for basic control system or educational processor. So we are successfully build a CPU with the 32 bits, design a CPU with a 32 bits with the logic operation, arithmetic operations, and we also learn how to make block diagrams and truth tables, and we learn more about ALU, the last arithmetic logic units, how to make a coding. So that's all. Thank you. And yeah.